pattern will be in the drag box. So that's why it is called in one location, it it will be there. It is called, that's why it is called single piece pattern or solid pattern. Entire shape of the component will be in drag box, so only one box will be there. So it is inexpensive. And examples where we use application of this solid piece pattern: bodies of regular shape, symmetrical shapes, small bodies. Next one is stuffing box of steam engine is generally used, manufactured by, the pattern is manufactured by single piece pattern. Stuffing box of steam engine. Next one is multi-piece pattern, or it is also called split piece pattern. Split piece pattern. Patterns of intricate shape components, complex castings cannot be made in one single piece pattern, so that's why we go for multi-piece patterns. So complex patterns are manufactured. So we combine 2-3 pieces. So upper and lower parts of the split piece patterns are accompanied to pump, as I mentioned you, cope and drag box. So the some part of the material will be, the pattern will be in cope box and some part will be in drag box. So the separating line is called parting line, and to connect those two boxes, it is called dovetail pins are used actually. So split piece pattern is one of the important application for especially complex shapes. Patterns which are made of two or more pieces. These pieces are aligned together or joined together with the help of dowel pins. These pieces are joined together with the help of dowel pins. With dowel pins. So as I mentioned you, cope and drag box. So the pieces will be, one piece will be in cope box and drag box. These two combine are connected with the help of dowel pins, and we'll ram that and we'll prepare the first cavity, and then we'll remove the pattern and we'll pour molten metal. So we will get the casting. That's why it is also called split piece pattern or two piece pattern. Instead of single piece, it is two pieces. So this is one application. So examples: hollow cylinder, taps, stopcock, are similar complex shapes generally manufactured by split piece patterns. Next pattern is sweep pattern. Sweep pattern is used for symmetrical shapes. So what happens is, it rotates because of symmetrical shape you prepare half component, and in several cases it could be economical to save the money and efforts of making the full pattern because of symmetry. The cavity in such case, in the case of the sweep pattern, is made by half pattern and rotate it around the vertical axis, so you will get the full pattern empty space. So that's why sweep pattern is one of the advantages compared to the other patterns. So small simple example of diagram. This is a wooden box. So the pattern shape is so in the middle it has to be connected to one vertical rod, so it will rotate along with the rod around the rod. So this is a wooden piece, so once it rotates it creates a shape, a hole of the symmetrical component. So this is a sand mold, and this is mold, sand mold. This is a wooden pattern, symmetrical pattern. So prepare half pattern and rotate it along about vertical rod, such that you will get the final pattern. So it is only used for symmetrical patterns. Next pattern is gated pattern. So here different types of sections of gates are connected, like if you want to produce so many castings at one go, so you have to be connected all in one gate. Like for example, suppose so in the same diagram, instead of one casting component, so this is a gate, and for each gate it will be connected to a number of castings. So this is a gated pattern. All of same component. So this is the gated pattern. All these are gates. So once you will get, so these are castings or patterns. In one go it will produce 6 components. So like this is for mass production of small components. So we have completed the pattern, types of patterns, and pattern materials. Now we have to discuss what is the size of the pattern, how to pattern alliances. For that, size of pattern equal to size of casting plus or minus alliances. So what is alliance? Alliance is extra amount of space provided to compensate the expansion or compression of the while cooling of the molten metal actually. So here size of the pattern equal plus or minus. You may have thought that why it is negative. It is for a special case of metals where on cooling they expand, on heating they compress. Especially wrought iron is one of the metal which have negative linear expansion coefficient, which behaves differently from other metals. And there is another metal invar where their linear expansion coefficient is 0. That means there is no expansion or contraction even after cooling or heating. So to consider all those, so we have given plus or minus. So there are different types of alliances. First one is shrinkage alliance. Shrinkage alliance is, why do we need to provide shrinkage alliance? So to understand that, first you need to know how the molten metal from the pouring to cooling conditions. The point is A, B, and this one is C. So this is C and this is D. Sorry. B. This is A. This is liquid plus solid. This point is called melting point. Of the metal, where change of state takes place. So any metal from A to B, pouring temperature to melting point temperature. So on cooling, so y-axis is temperature, x-axis is time. So on cooling, that after some time it will reduce the temperature, right? So AB, from pouring temperature, whatever the molten metal you are pouring to, it will come to melting point temperature. BC is the phase transition state. Phase transition from liquid to solid. So AB is solid state, AB is liquid state, BC is liquid to solid, CD, once the phase latent heat takes place, that means the total conversion of liquid to solid, then solid cools from melting point, cooling from melting point temperature to melting point to room temperature. Which is in solid state. So in all these three stages, the shrinkage of the molten metal takes place. So all three in above all three stages, metal shrinkage takes place. But only we consider, so A and B and AB and BC, liquid and liquid shrinkage. AB is liquid shrinkage, AB, and liquid to solid shrinkage is compensated by using riser. By using riser in the mold, sand mold. Riser acts as a reservoir. Solid shrinkage is compensated by providing shrinkage alliance. Because in solid state the metal which is in riser will become solid, so it can't compensate the shrinkage happening in the cavity. So because of that we need to provide alliance for the pattern itself. So for example, suppose this is a some rectangular pattern is there, and I am sending molten metal. This is a riser. Riser acts as a reservoir. It stores molten metal and sends molten metal into the cavity whenever the to compensate the liquid and liquid to solid shrinkage. So once molten metal enters into the cavity, this is cavity. So once molten metal enters into cavity, after filling the cavity or filling the pattern, the cavity which is formed by the pattern, if the molten metal enters into the riser, so the liquid and liquid solid shrinkage which is happening in the cavity is casting space is compensated by the liquid stored in the reservoir riser, which is as a reservoir. So once the entire metal liquid is solidified, so at that time during solidification from melting point temperature to room temperature, so there is shrinkage takes place. So that shrinkage is not compensated by the molten metal which is in the riser. To compensate that, we provide shrinkage alliance to the pattern. That means if suppose for example a metal is shrinkage, it is reducing volume while cooling, that means we need to provide higher size of the pattern such that even after shrinkage we will get the 50-50 or whatever. Suppose for example 50, if I want to produce a casting of 50-50 square, 50-50 casting size, to get 50-50 casting size we need to use shrinkage alliance on each side. For example, shrinkage alliance is represented as 1 in M50 or 1 by 50. So this means 1 mm of shrinkage alliance for 50 mm of side. So in the present example, if you want to produce a casting of 50 by 50, you need to increase 1 mm on all sides. So you need to create a pattern of size. Pattern size has to be 51-51. So because we are giving 1 mm shrinkage alliance, so if the pattern is 51-51 size, even after shrinking 1 mm on each side, it will become 50-50, right? So this is about shrinkage alliance. Next alliance is machining alliance. Machining alliance is once the casting component, if you remove after completion of the solidification, if you remove the casting component, it will be there, the surface won't be as smooth as the required. So there has to be rough surface will be there because of sand molds. So to get the excellent surface finish, we need to go do finishing operation. So to machining especially, we have to machine the component on all sides such that we will get the very excellent surface finish component. So for that we need to have, if you want, machining means you are removing material from the casting. So that suppose if you are removing 1 mm means you have to, it has to be more 1 mm more. Suppose the casting of 50-50 you want to final product, so you are removing 1 mm from each side or 2 mm depending upon the type of casting. So then it has to be the casting from the mold has to be 50-52 if it is 2 mm for each side. Machining alliance is provided to compensate the machining to compensate the material lost in machining. Machining alliance is represented as, for example, 2 mm per side. So if for one side we have to give some, we have to remove some material. So 2 mm per side. Suppose if you take the same component 50-50, if you want the final product, so you need to have a pattern of considering only machining alliance without considering shrinkage alliance. We need to provide, it has to be 54-54 mm. So to get casting to get final finished component, of size 50 cross 50. Considering only machining alliance, two mm per side, the size of pattern is so 54 54, because so even you can try with different parametric. So 2 mm per side, right? So for example, this is 50, and here 2 mm. Similarly other side 2 mm. So that's why the sides will become 54 54 if it is cube. So we are here providing only machining alliance. Suppose if you provide even shrinkage alliance also, then the sizes will be different. Okay, so the shrinkage alliance actually in shrinkage alliance depends upon the coefficient of linear thermal expansion. If the coefficient of linear thermal expansion is more, that means there is more expansion or contraction of that material. If that is 0, means there is no change of the material, size, shape of the material, size of the material with temperature. So if that is negative, means it expands on cooling and contracts on heating. So for example, that is negative for grey cast iron. So all the metals expand on heating, whereas only grey cast iron expand on cooling. That's why the alpha is negative, and as well as shrinkage alliance is also negative. Suppose in the above problem, if you provide machining shrinkage alliance also in the above problem, if we consider shrinkage alliance also, then the size is then the size of the pattern is so considering shrinkage alliance is in bracket, considering shrinkage alliance is 1 mm per 54 mm. For simplicity case, I have written like that 54. So here you have to again increase 50, instead of 54 you have to write 55. So pattern size equal to 55 cross 55. So this 55 cross 55 dimension we need to consider if we are taking shrinkage alliance as well as machining alliance both. Shrinkage alliance 1 mm per 54 mm and machining alliance 2 mm per side. If we take these two alliances, then we our initial size of the pattern has to be 55 mm to get the casting of 50 cross 50. So if you want to get the cube of 50 comma 50, you need to give initial dimensions of the pattern 55 cross 55.